I wasn't going to be around, so I fixed it for tomorrow first. Then once I decided I'm here, I thought I will have another session. Anyway, this is the last week, so we will, as you would have heard, you will have a final exam next Sunday. I'll give it in the morning, 10 o'clock, and ask you to submit by 10 p.m. You probably don't need more than 2-3 hours. And I have a bunch of questions, and I ask you to show they are true or false with some justification. Yeah, that's all the thing is about. And if necessary, I may have a Viva individually meet some people if I want to clarifications on the questions, answers, for example. Okay, good. So let's get started. So what I plan to do is to talk about the solutions for the NP complete problem assignment, and then leave it open for any questions otherwise. Okay. Okay. So first question on NP completeness asks you to show that set cover is okay. Let's see some echo. No, it's fine. Yeah. So anyone wants to suggest solution? How do you show? First, it's an NP. By the way, we have also uploaded all the solutions in the website for all 6 assignments now. And the marking is happening. You would have seen the marks for the first 3 out there. Yeah. And my plan for the final marks is I will take 60%, okay, maybe for final, 40% for the assignments. I pick the best 4. Assignments marks as the 40%. Yeah. Okay. So how do you show set cover is NP complete? First step, you want to show it is an NP. Which means you have to give a proof, some witness, and then a verification algorithm. Anybody wants to tell me how to show it's an NP?
Given any k subsets, we can take the union and verify whether it is equal to x or not.
Right. So that's just a polynomial thing. So the witness or the proof is some subset, and you take the union and show it's in it. It covers the universe. What about what is the reduction from?
From vertex cover problem, sir.
Okay. Since it's a covering problem, you should relate to what other covering problem we've seen. We've seen vertex cover, so take it from vertex cover. So we have a graph. Vertex cover, what is the input? Graph and an integer k.
Integer k.
The question is, are there k vertices that cover all the edges? And we want to reduce to this set cover problem. So that means you should have x and an f and a k prime. So what is x, what is f, what is k prime?
X is set of all edges in the graph.
Yes, because we are trying to cover edges using vertices. So our universe we are trying to cover a set of edges, and f would be. So remember, f has sets which are all subsets of E. So what should each subset correspond to?
The set of all edges incident on each and every vertex would be the subset.
So we will have a set for every vertex. And let's call it some E of V. Instead of all V comma W, VW is an E. It is incident on V. And what is K prime? Because remember the set cover instance requires three things. You want to show that if G has a vertex cover of size K, if and only if there are some K prime sets in F that will cover your universe X. What is that K prime?
K.
K, exactly. Okay, and you can easily show that. So G has a vertex cover of K vertices if and only if XF has a K-sized subfamily covering X. This requires a proof, but pretty standard, right? You pick some K-sized vertex set that cover the edge set, then the corresponding K sets in the family would cover your universe, which is the edges, and similarly the converse, because that's the way we have constructed it. Okay, good. The second question is all about subgraph isomorphism. So let me spend some time talking about first isomorphism, right? What does it mean by two graphs are isomorphic? It essentially means that the two graphs are the same. Okay, if you have two graphs which are isomorphic, means two graphs are same. For example, if I have a graph like this, I might have drawn differently, but you can see that they are same. So what is the formal definition of isomorphism? Two graphs are isomorphic means that there is some correspondence. So I might have 1, 2, 3, 4 as the vertex set here. I might have an A, B, C, D here. You should give some mapping between the vertex set of the left graph and the right graph, such that they are the same, means that whenever there is an edge in the left graph, the corresponding mapped vertices should have an edge. And conversely, if you don't have an edge in the graph, the corresponding mapped vertices should not have an edge. That's all. Okay. So in this case, suppose I map 1 to A, 2 should get mapped to B, 3 should get mapped to D, because 3 is adjacent to 1, and so you should be adjacent to A, and then you are not B, so it's D, and 4 gets mapped to C. If you look at this mapping, then whenever there is an edge between I and J in the left graph, there is an edge between f of I and f of j. And where there is no edge between I and j, there is no edge between fi and j. Okay, so this is what isomorphism is. Now, given two graphs are isomorphic, is it NP complete? Is there a polynomial time algorithm? This is one of the big open problems. Okay, graph isomorphism. P, this is a big open problem. People believe it is a polynomial time algorithm, It's not NP complete. There have been very efficient algorithms, but not yet polynomial time algorithm. This is one of the big open problems. Okay. But we are not asking for graph isomorphism. We are asking, this question is about subgraph isomorphism, which means I have a graph H and I have a graph G. I want to know whether there is something here, whether H is sitting inside G. That's the question. So you still need a mapping, but not from H to entire vertex at G, but to some subset of vertices, such that whenever there is an edge here, there is an edge in that subgraph. That's the question. Okay, this turns out to be NP complete, and we'll see why. First of all, how do you show it is an NP?
When the mapping is given, we can easily check.
Okay, so what is given? What is the proof? So I have H and have G. Okay, so what is the proof for the S answer? Mapping between what?
Mapping between the vertices of H
And
and the vertices of G.
no,
The
that is
subset.
that is isomorphism. We're not talking about it.
Okay.
H is a smaller graph compared to G. So you can't even map to G. You see my picture. So the proof should contain two things. What are the two things?
Edges of G and edges of H, sir.
No, H is given, G is given.
Okay.
And the question we are asking is H sitting inside G as a copy? Is there a copy of H in G? So H may have 5 vertices, G may have some n vertices. Okay. So I ask, so let's look at some example, right? Suppose I ask, maybe this is my H, and G may be something like this. Okay. So let's call this A, B, C, D. Yeah.
Mapping between vertices of H to 4 vertex subset of
Exactly. Whatever that subset of vertices. Okay, so this is my thing. And now I ask, is H sitting inside G? And if you want to prove yes, what would you give? What is the mapping in this example you'll give?
the vertices 3, 4, 5, and 7.
So first you should give the subset 3, 4, 5, 7. That is one subset you give. And then you have to give a mapping. What is the mapping?
A
So you say A goes to 3, B goes to 4, and C goes to 7, and D
goes to 5.
So the proof that it is an NP, by the way, anyway, the solution is uploaded already, should contain a subset of V of G. Let's call that some S, and B, a mapping between V of H and S. Okay, so it's basically I want to know whether H is sitting inside G. You give me some subset here and say yes, you have a copy of H here, and here is the mapping. So you have to give me an S and you have to give a mapping. May I just verify that that mapping satisfies the property that whenever there is an H, there is an H here. Whenever there is no H, there is no H. Okay, so again, are the two graphs isomorphic is open. We don't know whether there is a polynomial time algorithm, is it NP complete. People believe it's polynomial time solvable. But here we are asking, is H a subgraph of G? Is there a copy of H sitting in G? Okay. That problem, it is an NP. Now to show NP complete, what do you do? What kind of problems have you seen? In a big graph, you are looking for something. So, where do you reduce from?
Click.
Yes. Reduce from click, right? So, what is input here for click? It's G, V, E, and a K. You're asking in this graph, is there a click of size K? Now you have to reduce it to some G and a H and check whether G has a subgraph isomorphic to H. So, what is H here? What is G?
H is a click
Yes. On how many vertices?
on
K
K vertices.
K
Yes,
vertices.
exactly. So you have a click on K vertices. G is my original graph G. Then you ask, is there a click? Is there subgraph of G isomorphic to H? And then the proof is straightforward, right? Can you think of some other problem from which to reduce? Click is one, but actually you have more choices here.
Even independent set.
Independent set, because it's the same thing, right? You're asking, is there a subgraph isomorphic to G? So independent set we have seen is hard. So that's another example. Okay, any other example?
Hamilton cycle.
Yes. You can say I have a G and you can look at a cycle on n vertices as your H. Then asking, is there any subgraph of H in G? The same as does G have a Hamiltonian cycle? You can even reduce Hamiltonian path, for example. So this question is there some structure I am looking for in G? Which we have seen in so many examples, which is NP complete. And so it follows. So you can reduce click or independent set or Hamiltonian path. Okay, good. So now the second question is about trying to show something is true or false. Can somebody tell me what are the questions?
Sir, I have a doubt in the previous problem. We haven't said that it's a proper subgraph. It's just a subgraph, right? G can be H as well. So,
Yes.
so in which case, graph isomorphism should also be NP complete, right?
That's special, right?
Okay.
Okay, so that's a good question. We are saying a general problem is NP complete, where H can be anything. You want to know whether it is sitting inside G is NP complete. Now you are saying I have a specific graph where H has certain n vertices and is it isomorphic? Then it may or may not be. It is like when we talk about vertex cover in general graph, it's NP complete. But suppose your graph is bipartite, it may not be.
Yes, sir.
So similarly, when I give you two general graphs H and G and I ask whether H is a subgraph of G, that's NP-complete. But for the special case, when H is equal to a graph on the same number of vertices and the same number of edges, this is the same as isomorphism question, and that we don't know. It could be easier. Okay?
Okay.
Something special could be easier.
Okay. Okay.
Yeah, that's a good question, though. Anyway, yeah, right. Okay. So the next question I had this true or false questions. Let me see if I can get my problem sheet. Or if somebody can tell me what the questions are.
Given a graph G and an integer K, determining whether G has a vertex cover on at least K vertices is NP-complete, sir.
Correct. Okay. So the key thing is at least K. Is that NP-complete?
No, sir.
No.
Okay. Arunachalam, why not?
Sir, whenever G has a vertex cover, it is at most K vertices.
No. Most K is the problem we have seen. It is NP-complete.
NP-complete, yes, sir.
But suppose I ask you, I give you a graph on n vertices.
Okay.
And given integer K,
Okay.
and I ask you, is there a vertex cover on at least K vertices?
So it is a decision version, so it is not NP-complete.
No, what do you mean? Decision versions is always what we talk about. Vertex cover is also a decision version.
But it can't say the K, sir. It is at most. It can't be beyond K.
But why not? I'm just saying, let me ask the question. Suppose I give you a graph on n vertices,
Fine.
and I give you an integer K, and I ask you, do you have a vertex cover of size at least K? Can you answer in polynomial time?
Yes, sir.
Yes, you can do it.
Arunachalam, why?
Sir, when you are saying a vertex cover with K, it has to be done. We can find K, but the thing was you are saying at least K, the minimum value to be put into K.
No, wait. So you have to think about this. Vertex cover problem is a minimization problem.
Minimization, yes.
So let's say I have this graph. Let's look at an example. I have a graph where n is 200 and k is some 30. And I ask, is there a vertex cover on at least 30 vertices? Okay, let me ask a different question first. Instead of 30, I say 300. What is the answer? I give a graph on 200 vertices and I ask, is there a vertex cover on at least 300 vertices?
No, there is
not.
It is. Yeah.
I mean, what is the answer to this question? Forget about polynomial time or not. I give a graph on 200 vertices.
Yes.
And I ask, can you give me a vertex cover on 300 vertices in this graph?
Not possible.
Not possible. Trivially, no. So I don't even have to think about it. The answer is trivially no, right? But suppose I ask you instead of 300, I ask you 30. But important thing is at least 30. So think a little bit. I give you a graph on n vertices, and my k is smaller than n, and ask you, can you give me a vertex cover whose size is at least k?
Sir, it is a minimum. You are saying at least K. It will start with 30, sir. It can go with any other thing.
Yes. So can you give me a vertex cover with size greater than 30? in this graph. And we don't even have to look at the graph, right?
Yes, it can be anything.
So give me
Any.
an example vertex cover whose size is bigger than 30. Anybody else? I mean, Devi, maybe she can tell.
Yes, sir. Set of all vertices in the graph itself is a
Take the entire vertex set. I give you a vertex cover of size 200, right? That's a vertex cover of size at least 30. Is that clear?
But
So
what's the need of getting entire vertices 200, sir?
because it is at least 30. You wanted at least 30.
Yes, at least 30.
Trivially, there is a vertex cover of 200, which is of size at least 30.
But the aim of vertex cover is not the goal.
No, but not the aim of this question. Yes, that is why we ask the question at most k. That is more meaningful, more interesting, and that is a hard question. The moment I ask at least k, it's a trivial question. That's why it's not an interesting question. If k is larger than n, you say no. If k is smaller than n, you say yes. Always. You don't even have to look at the graph. So, whenever you're talking about a minimization question, that's why we always ask at most k, and that is a hard one. For minimization problem, so it's like I give you a graph and I ask, is there an independent set of size at most k? Can you give an independent set of size at most k in a graph? Anybody? Wait, again, Devi Amni should wait, but others I want to see. Is there an independent set of size at most 50? Suppose I'm asking this in some large graph on 200 vertices. I'm asking, is there an independent set of size at most 50?
There will be more than that.
Can you give what is the answer to this question?
Yes.
Yes. What's an answer? How? Why?
Maximum there will be 200.
No, but I'm asking at most 50. The key thing is at most pay attention. I want you to give me an independent set. You know what an independent set is, right? Subset of vertices which are mutually non-adjacent. I want something, the number of them must be less than or equal to 50. It can be much, much less than 50. So what would be an example independent set? Yeah, Devi?
every singleton vertex is a
Singleton vertex. I give you one vertex and say here in this graph, it's an independent set of size at most 50. Right? That is why when it comes to maximum independent set clique, the at most question is uninteresting. You ask at least. When it comes to vertex cover, the at least question is not interesting. You ask at most. At most or even equal to is a hard enough question. Is there an independent set of size 50? That is hard. But if I say less than or equal to 50, that's trivial because I can just give one vertex and say, here it is. It's of size at most 50. Okay. That's why, equal to question is interesting. It can be hard. But when you talk about less than or equal to, greater than or equal to, you have to understand, is it a minimization problem, maximization problem? I mean, for every graph, you can ask both. Even for clique, I can ask for min clique, min independent set, but they are not interesting because they are trivial. Similarly, for vertex cover, I can ask for max vertex cover. That's not interesting because the entire vertex set is a max vertex cover. Okay, so the question you have to pay attention to less than or equal to or greater than or equal to. Okay, is that clear? Did I confuse you more? Debajyoti, Arunachalam?
Yes, that's fine.
It is okay, sir. Okay.
Okay, so this is subtle, some sort of a boundary thing you should pay attention to.
Sir, as you told, a singleton graph, I think line graph is also like this. Huh?
Not singleton graph.
Yeah.
Graph is an input graph you are given. I am looking for in that graph a subset of vertices which form a independent set or a clique. So if you ask for a minimum size, that's trivial for clique or independent set. Because singleton, one vertex is. Okay, so input is G and K, and you're looking for a clique or independent. So exactly K is fine. That's a hard problem. Greater than or equal to K is also interesting when it comes to clique or independent. But if you say less than or equal to K, it's not an interesting question. It's a trivial question, solvable in polynomial time. I don't even have to look at the graph. I can just give the answer. Okay, what is the next question?
Problems in NP are not known to have polynomial time algorithms.
Yeah, okay. This is a common confusion. The moment people think it is NP, they think it's not solvable in polynomial time. Okay, so what is the answer to this?
False.
Why?
Because we have checking whether a graph is connected, that is also in NP.
Yeah, the entire P is sitting in
P is
NP.
a subset of NP. P is
So
a
many
subset of
problems are there.
So in NP, there are problems that are solvable in polynomial. Don't think that NP means, oh, we don't know anything about polynomial algorithms for this problem. NP stands just for non-deterministic polynomial time or for verification. Don't get confused with not polynomial time. And C was, yeah, C was about Hamiltonicity, right? I think I probably even discussed it in class. So we said Hamiltonian cycle problem is an NP, has no polytime algorithm, so this problem is an NP but not in P, therefore P not equal to NP. So what is it? I mean, it cannot be true because P NP equation is a famous open problem. So what is wrong with this argument?
This is false.
Last conclusion is not true.
What conclusion is not?
P not, therefore, P not equal to NP.
Why? Because I gave you a problem which is in NP and not in P. So how can they be equal? If I have a problem which is in NP but not in P, that means P and NP are not the same, right? Just said theoretically. Okay, I'll just be back in a minute. Okay, so what's the problem?
So till date, we don't have a polynomial time algorithm. So we can't say that it is not in P. We don't know the answer yet.
Exactly. That's that. We only have no known polynomial time. Doesn't mean that it is. To say that it is not in P requires a proof that it cannot be in polynomial time. Okay, so that's the problem. Okay, And the final question was about why the primality algorithm is not polynomial time. Yeah, so why is that not a polynomial? Again, I've discussed it in class, I think.
Yes, sir.
Yeah. So let's see if anybody else. I'm trying to see whether people are watching my videos also.
Yes, sir. Here, rather than taking the input size as n, here we need to take it as the number of bits that are needed to express n, which is log n.
Correct, exactly. So n is not the input size, n is the input. The input size is log n. So your algorithm time, which is n, is exponential in the input size. It's not a polynomial time algorithm. But then one could ask for an algorithm like for sorting. What is input size? Why is there your input size is n?
There we need to consider the number of elements rather than number of bits.
Yeah, there also you consider number of bits, but there are n numbers and each one requires a certain bit size to represent each number. So totally it's n times the largest number or something, but it's still certainly larger than n, not just the n which is log n. Okay, so let me now stop here. Give me 1 minute, and I will be open for other questions for the next 15 minutes. Then, yeah. Okay, any other questions on anything? So for people who joined late, I said my final exam will be given next Sunday. I have some number of questions. I want you to say they are true or false with some justification. That's the exam. I don't think it should take you more than 2-3 hours, but I've given you some 12 hours just to, because you may pick your 2-3 hours window sometime. Okay, any other questions or comments?
Sir, to show a problem is NP complete, we need to show two steps. First is to show the problem is in NP, and second step is to show that any non-NP complete problem can be polytime reduces to this problem. So in assignment you gave some problem that, but because before that we need to discuss some very common problem like clique and independent set or TSP and Hamiltonian cycle, and that how with the help of these two property we can show this. So either there is this type of question that show that TSP is a NP complete, or there is this type of question that it is also told that show that TSP is a NP complete from the reduces from the Hamiltonian cycle. So these two type of question may we can see. So can you once more discuss these two steps for this type of basic problems?
Yeah. So first of all, yes, it's not easy to figure out which problem to reduce from. So that's why sometimes they just give you reduce from here to here. And often, like we saw for set cover, you see that set cover is actually a generalization of vertex cover, because set cover models various other problems. So if a simple problem is hard, the general problem will be even harder. So that's the motivation. Okay. So let me actually give a reduction from Hamiltonian cycle to TSP, right? And maybe we'll also show why TSP is in NP and so on. So you have to be, when it comes to proofs, you have to be absolutely clear about the statements, what is given, what are you trying to prove, all that kind of thing. Okay. So first, let's try and show TSP problem is in NP. Before that, we need to know what is the TSP problem. What is input and what is the question? What is input?
Given n cities
Okay.
of a undirected weighted graph.
Okay, so you have an undirected weighted graph, and then you have some distances.
Yeah.
On edges. And what is the question?
That the salesperson have to visit every city exactly once and have to come back to the starting point.
With minimum distance.
With
Yeah.
minimum distance, right? And how do you make it as a decision question? Because we don't want to deal with minimization problems. So what is the decision question?
Okay, say I have given some distance, say 100.
Yeah, K. So your input contains of a graph, distances on edges, and some K. And you ask, is there a Hamiltonian cycle with total distance at most K? You have to be precise about this statement. What is input, what is given, what are the questions. So we want to show this problem is in NP. So to show NP, you need to give, so to show it is in NP, give a proof for S answer. So suppose the answer is yes, what is the proof, and then what is the verification of? You should give a proof which should be easily verifiable. Easily meaning polynomial. So what is the proof for this? Proof or a witness or certificate, whatever they call it. Yeah, so suppose you want to tell me, yes, in this graph, there is a Hamiltonian cycle whose total distance is at most K. How will you convince me? What is the proof? Right? I mean, here is a graph. You want to tell me that there is a Hamiltonian cycle whose distance is at most K. What would be what would be the certificate? See, if you want to show that a formula is satisfiable, the proof is some assignment that satisfies all the clauses. If you want to show a graph has a k-sized vertex cover, give a subset that covers all the edges. The verification algorithm will just check whether the subset covers all the edges. So here, what would be the proof? What, people have gone to sleep or what? It's not a hard question I'm asking. We are, reduction is a different thing. Here I'm asking, given this graph on 10,000 vertices, you are telling me that there is a Hamiltonian cycle tour which will, visit all the vertices and come back with some 25,000 total distance. So what will you show? How do you prove it to me?
Given any subset of at most k vertices.
No, we're talking about Hamiltonian cycle. You're not talking about k vertices covering any edges or anything. Yes, Arunachalam.
To visit exactly n vertices.
Hmm.
With
You will give me a Hamiltonian cycle. That's the
Yes.
proof, right?
Yes.
What is a Hamiltonian cycle? It is some ordering of the vertices. You say I start from 1, go to 7, from 7 you go to 3, 3 to 4, 4 to 2. I mean, imagine an example graph. You want to show there is some cycle, right? So if you have to show that, okay, so if this is graph, A, B, D, C, E is one cycle. You can also say A, E, B, D, C, A. Okay, this is another cycle. There may be other cycles. You pull out one such cycle and say, here is a cycle whose total cost is at most k. That's the witness. That's the proof. And what do? I verify every consecutive edges, make sure they are edges in my graph, count the total distance, and convince myself that it's less than or equal to k. So that is a polynomial time verification algorithm. So you have to give me a proof, which is a Hamiltonian cycle in this example, with total cost at most k, and which verification algorithm checks that it visits every vertex, it's a cycle, total distance is at most k, and all that. That's a proof. So a cycle.
Sir, I have a doubt here.
Yeah.
Instead of giving a cycle, I can give a set of k vertices as an input. Like that can be checked whether it forms a cycle. In fact, Hamilton cycle as well.
No, graph has n vertices.
Yes, sir.
How can k vertices?
I'm sorry, it is on n vertices.
It must be n vertices.
An order of vertices can be given to us.
An order. Yeah.
Yes.
What is the Hamiltonian cycle? Okay. Some permutation.
Yes, sir. Yes.
That's it. That is the input, a permutation of 1 to n. And you give that permutation as the output, as the proof, which is same as giving us, I verify every pair, make sure that's an edge, sum the total, and make sure it's at most k.
Okay.
So it's equivalently, or a permutation on 1 to n.
So there should be a pair. There should be edge for each and every pair. That is the most important point, sir.
That's a verification algorithm will do the job. Yes, exactly. It will ensure that the permutation you've given, every successive pair is an edge. Together, it adds up to k is the verification algorithm.
That's it.
Verify in polynomial time, because the polynomial that's only n time, right? Check every consecutive thing, adds the sum and finds that it's at most n. That's a order n time. Now, to show that it is NP complete, I have to show that if I solve this problem, I can solve some other hard problem. That some other is already in this case given to you. It's a Hamiltonian cycle. So, to show hardness, so that if TSP has a polytime algorithm, I can use that as a subroutine to solve Hamiltonian cycle. So now let's pick the Hamiltonian cycle problem which I'm trying to solve. We have to have a clear understanding of what the problem is. Okay. So I have this Hamiltonian cycle instance as a graph GB. The question we want to solve is, does it even have a Hamiltonian cycle? Clearly, we expect this to be a simpler problem because TSP among all Hamiltonian cycles finds the one with minimum distance. Here, so in fact, for TSP, we can even assume it's a complete graph. Can assume it's complete. Because whenever there is no edges, you can put some infinite cost or something like that. So that means there is always a Hamiltonian cycle in the TSP instance because it's a complete graph. The only thing is the distance can be huge. Among all Hamiltonian cycles, I want to find something the least cost. So now I want to show that I want to solve Hamiltonian cycle. Given an arbitrary graph, does it even have a Hamiltonian cycle is what I want to solve, right? So I take my graph, do some reduction, and give it to the TSP algorithm. TSP algorithm needs G plus distances. Some G, it may not be the same G, it's your choice. You give it and it comes back yes or no. Based on that, you are supposed to figure out whether your original graph has a Hamiltonian cycle or not. So now what surgery, what modification do you do your graph? This, and it also requires a K. It requires a G, it requires distances, it requires K. TSP algorithm will say yes or no. Now, in this graph, you want to know whether you have a Hamiltonian cycle or not. So what will you do to this graph to use the TSP algorithm? As far as TSP algorithm is concerned, it requires graph, it requires distances on the edges, and it requires a K. Then it comes back and saying, is there a Hamiltonian cycle of total distance at most K or not in that complete graph? So how do you take your graph, modify it into a complete graph, put distances, come up with a K, so that the TSP algorithm's answer can be used to determine whether the original graph has a Hamiltonian cycle. Yeah. Any thoughts? Somehow you have to take your graph where you are interested in even testing whether there is some Hamiltonian cycle, add edges, put some cost, blah, 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 and then check whether there is a Hamiltonian cycle with total cost at most K. You have to also come up with a K. Based on that, you determine whether G has a Hamiltonian cycle. So what do you do? Yes, any thoughts? How you have to first make it, you have to put distances on the edges. What would you want to put? So here is my G, which has some edges. You want to put some distances on the edges, make it a complete graph. How do you do it? What are some ideas to do that? So if you make it a complete graph, add some missing edges, then the new graph is going to have some Hamiltonian cycle, even if the original graph does not have it. And you're going to do some control with the total distance measure. That's the whole point. Okay. So tell me how to add edges.
We can add edges with infinite weight.
Infinite distance, right? Whenever the original graph does not have any edge, I will add an edge with infinite distance, some very large distance. And what are you going to put distance for the original edges?
1.
1, right? So now what we'll do, we're going to define dij equal to 1 if my ij was e and infinity otherwise. Good. So now I have a weighted graph ready to be given to TSP algorithm. TSP algorithm will come back. Remember, it's a decision version algorithm. So it will come back and tell you there is a tour with costs at most something. That's something you have to give. What is it something you want to give? What is their K? So
N
let's
plus
see.
1.
N plus 1, is it?
Yes. Yes.
Okay, why n plus 1? So let's say original graph, suppose it has a Hamiltonian cycle. What would be the cost of that cycle in this weighted graph now?
N.
N,
Sorry,
right?
N one sense.
Yeah, because there are n edges. Okay, and if your Hamiltonian cycle uses one of the newer edges, non-edges of the original graph, what will become the cost?
Infinity.
Infinity.
Infinity. In fact, you are clear it will become more than n.
Yes.
Okay, it will be infinity, true, but because first of all, the cycle has n edges. Any Hamiltonian cycle has n edges, and the costs are either 1 or something big. In fact, you don't even need to give infinity. You can give 2. 2 is also fine. Okay. So I can replace. Suppose I do this by 2 and give kn. Then G has a Hamiltonian cycle. Implies the TSP has a Hamiltonian cycle with total distance n. And G has no Hamiltonian cycle. TSP will always have Hamiltonian cycle. Remember, because you added all the edges and you made it a complete graph. But any Hamiltonian cycle in the TSP, which you have constructed, will have total distance
Strictly greater than n.
strictly greater than n. It's greater than or equal to n, strictly greater than n. Why? Because any Hamiltonian cycle will have n edges. But if you look at the weights, not all can be 1, because if all are 1, that is a Hamiltonian cycle in the original graph. So at least 1 must be 2. At least 1 must be 2. So the total distance will be, there are n edges. Each edge has weight at least 1. And at least one of the edges has weight at least 2. So the total will be strictly more than n. So now what is your algorithm? You take your graph, make it a complete graph, put a weight of 1 for the original edges, put a weight of 2 for the remaining edges, and now you give it your TSP algorithm. It comes back and give the total cost to be n. If it comes back S, you know G has a Hamiltonian cycle. It says no, G does not have a Hamiltonian cycle. That's it. In fact, if you notice, we have shown something even stronger. We said that TSP instance, where the edge weights are just 1 and 2, even that's NP hard. Okay. Yeah, so this is it. It's all about reducing one problem to another.
Sir, in your lecture, you have used the concept of graph complement.
Yeah,
So that is also used for independent set and click.
correct. Yeah. So you can use, so what, see, we have a problem A. So we want to show, suppose A is NP complete and you want to reduce to B. This is your goal. So what do we do? Take input of B, do something. This is the reduction. To get an input of A, assume polytime algorithm for A, get solution for, so this A is a function of the input of B. Solution for A, which is a function of B. From there, deduce solution for B. This is the strategy. This has, so somehow assume you have a polytime algorithm, use that as a subroutine to solve the other problem. For that, you need to take the input of the other problem, modify it somehow to meet the requirement of this algorithm. So in the case of independent set click, with the modification was just taking the complement. In the case of TSP Hamiltonian cycle, the modification is to make complete, add edge weights to whatever, and then so somehow you have to see that these problems are somewhat equivalent. In the case of vertex cover to set cover, we took the graph and created some sets from the graph. And then you can use the set cover algorithm to solve vertex cover. So what modification we do is not at all obvious. So for example, I would not ask general NP-hard questions in a test unless it's done, people have understood it well, then you can do it. Because it's coming up with an NP-hard, TSP Hamiltonian cycle is relatively easy. Subgraph isomorphism from click, those are easy questions in my opinion, because it's just, you have to visualize this problem as a stronger problem compared to the original problem, then you can modify it. In general, there are very complicated gadgets one needs to come up with, and it's not very easy to come up with NP-hard reductions. Yeah. But important thing is to understand the concept, understand some basic reductions, and depending on how much you want to familiarize yourself with that. Okay, so I'm going to stop here. I'm available tomorrow also as the last session for any general questions. So come prepared and we can have a session tomorrow. And you are also welcome to send me emails. In fact, Arunachalam sent mail about or WhatsApp message about subgraph isomorphism. I hope it's clear now.
Yes, sir.
Yeah, and feel free to send me mails even if you miss tomorrow's session. We can I can respond over email, fix some other time or something. Okay. So any other questions you want to toss now, which we can discuss tomorrow?
Tomorrow.
Think about, send me email.
Sure, sir.
Yeah. Okay. Thanks. Good night. Bye.
Thanks, sir.
Thank you, sir.